In this video we're going to look at a series of formulae known as the small angle formulae. Looking at the graph that we've got here, we've got the graph of y equals sine theta, y equals tan theta, and also the line y equals theta, where the angle theta is being measured in radians. Looking carefully at the graph, that we can see that for values of theta between 0 and somewhere around about 0.3, the value of tan theta is approximately the same as the value of theta, and the value of sine theta is approximately the same as theta. And these are two of the three small angle formulae. Now we can see how accurate these approximations are by producing a table of values showing theta, sine theta and tan theta for values of theta varying between 0 and 0.3, and this table of values certainly verifies that provided theta is between 0 and 0.3, then the value of sine theta is indeed approximately equal to theta, and the value of tan theta is indeed approximately equal to theta. Looking at the cosine graph when the angle theta is expressed in radians, it looks as if a parabola of the form y equals 1 minus k theta squared may be a better approximation to the curve than a simple straight line. In the video here we will see how the parabola 1 minus k theta squared approximates the curve y equals cos theta for values of k between 0 and 1. The video then suggests that for small values of theta, in particular values of theta which are less than 0.3, then the approximation cos theta is approximately equal to 1 minus a half theta squared seems to be valid. And we can check this again by looking at a table of values, and we can see indeed that for values of theta between 0 and 0.3, the value of cos theta is very close to the value of 1 minus a half theta squared. So the small angle formulae state that if the angle theta is measured in radians and is smaller than 0.3, then we've got sine theta is approximately equal to theta, tan theta is approximately equal to theta, and cos theta is approximately equal to 1 minus a half theta squared. Now so far we have used GeoGebra to motivate these formulae, and a more formal justification will be provided in the next video. Meanwhile though, we'll just have a couple of examples which make use of the small angle formulae. So in the first example, the diagram shows the curve of the function f of x equals cos x minus 4 sine x minus x, where x is measured in radians. We've got to use the graph and the small angle approximations to find an approximate root of the equation f of x equals 0. We can see from the graph that there is a root of the equation f of x equals 0 at somewhere around about x equals 0.2. Now 0.2 is certainly a small enough value of x that we can use the small angle approximation. We've got f of x is equal to cos x minus 4 sine x minus x. So we can say that f of x is going to be approximately equal to 1 minus a half x squared is our small angle approximation for cos x. Our small angle approximation for sine x is just x, so the small angle approximation for 4 sine x is just going to be 4x. And then we've still got the takeaway x from before, so we can say that f of x is approximately 1 minus 5x minus a half x squared. We're trying to solve the equation f of x equals 0, so it seems sensible to hope that the root that we are looking for will be close to the small root of the quadratic equation 1 minus 5x minus a half x squared equals 0. Solving that quadratic equation gives me roots of 0.1962 and minus 10.1962. We can see from the graph with the approximation 1 minus 5x minus 0.5x squared added to it that the approximation quadratic is good to the original function for small values of x, so it seems sensible to take the value 0.1962 as being our approximate solution of the equation f of x equals 0. If we move to the next screen, all I've done is I have enlarged the graph on the previous screen just to show what's happening between x equals 0.15 and x equals 0.24. The green curve is the original function cos x minus 4 sine x minus x, and the red curve there is the quadratic approximation to the green curve. So the red curve is 1 minus 5x minus 0.5x squared. And looking at the graph here, we can see that the quadratic root, which was 0.196, slightly underestimates the genuine root of the equation f of x equals 0. Later on in Maths Unit 3, you'll probably study some work on numerical methods. In particular, you'll study the Newton-Raphson method. And this would enable the root of the equation f of x equals cos x minus 4 sine x minus x equals 0 to be found even more accurately. It's worth noticing that there are many applications of the small angle formulae, particularly in physics and mechanics, and we're just going to have a look at one example at this stage. At their closest, the planets Venus and Earth are 40 million kilometers apart, and using a telescope based on Earth, Venus subtends an angle of 0.0087 degrees. Using these figures and the small angle approximations, we've got to obtain an estimate for the diameter of the planet Venus. So a diagram would clearly be helpful. T represents the telescope on Earth, and then we've got the green disk there represents the planet Venus, which is at a distance of 40 million kilometers away from the telescope and subtends this small angle theta from the telescope. So what we're after is a formula for the diameter of the planet Venus, and if we start off with just the radius of the planet Venus, then we can certainly say that dv is 2 times r. Using right-angled triangle work, we have got r will be 40 million times by the tan of a half theta. So we've got dv is 2 times 40 million times tan a half theta, which is in other words 80 million times by tan a half theta. Now we've got theta is 0.0087 degrees. So a half theta is 0.00435 degrees. But if we're going to use a small angle formulae, we must have our angles in radians. So to turn an angle in degrees, into an angle in radians, we need to multiply by pi and divide by 180. So we've got our angle, a half theta, is either 0.00435 degrees or it's 0.000076 radians. Now 0.000076 radians is certainly smaller than 0.3 radians, so we can say that the tan of a half theta is going to be roughly the same thing as a half theta. So we've got the tan of 0.000076 is going to be approximately 0.000076, which now gives me that the diameter of Venus is approximately 80 million times by 0.000076, which gives me an answer in the region of 6,100 kilometers for the diameter of the planet Venus. And that concludes our introduction to the small angle formulae.